Hello and welcome to this look at an applied water crystallization titration question. It's applied because of two things. Firstly, the fact that you're finding the water crystallization from a titration technique rather than heating to constant mass, which is more commonly found in water crystallization questions at A level. And secondly, because it's got an unusual scaling factor. Usually you come across 25 centimeters cubed in the conical flask, and it comes from a 250 centimeter cubed sample. Now, water crystallization from titrations can be done from either acid-base, which is this example, or it can be done from the more common redox titration examples. The redox titration type you'll find in the second year, and the acid-base titration type you'll find in both years. So this is our question. It gives a procedure that's described, and then it gives you the equation and what they want you to do. So looking at the procedure in the description, it's a good idea to try and visualize the various stages of the procedure in your head. Now you can write it down or scribble it down at the side of the exam paper on a spare piece of paper. It doesn't matter where you put it because it's not going to be considered by the actual exam marker, but it'll help you as the candidate visualize what all of those bits of information mean. So you start with 1.654 grams of a hydrated acid. That's probably going to be put into a weighing boat before it's put into some water, and the weighing boat would be sort of rinsed to make sure all of the solid goes into the water. Now this particular beaker here, it doesn't matter how much water is in here, because what you're going to do is put that into a volumetric flask and then make up to the mark. And in this particular question, where it said 23.80 centimeters cubed of this solution required 25 centimeters cubed of sodium hydroxide, what they mean is that the 25 centimeters cubed of the sodium hydroxide is in the conical flask, and therefore the solution is in the burette. So this amount, 23.80, came originally from this 250. That's what I mean by an unusual scaling factor. 23.80 doesn't go cleanly into 250. So we have to try and bear that in mind a bit later on. So looking at the calculation part, they want you to identify the value of X and hence the formula of the hydrated acid. So if we take the equation and do what's called data moles equation moles answer, I'm going to concentrate on the sodium hydroxide because that's what we have enough data for to work out the moles. So you put down the data that you have for the sodium hydroxide and use N equals V times C to work out the moles, which is in this case is 0.0025 moles. Now in the equation, the number of moles of sodium hydroxide to the H2C2O4 is 2 to 1. So you need to have that 0.0025 to get the number of moles of H2C2O4 that are reacting. So that's obviously 0.00125 moles. Now on the right hand side of the screen, I'm going to take this further to show you how you can work out the number of the value for X in XH2O. So as we've established, the moles of H2C2O4, excluding the water of crystallization for the moment, because that didn't react in the titration, it's just the salt itself did, is 0.00125 moles. Now what we do is we scale that up. So we're going to multiply that by the scaling factor. So you take the 250, which is the original sample dissolved in 250 centimeters cubed of water, and you divide that by 23.80, which is the amount that's needed to complete the neutralization. So that gives you the 0.0131302521. So I'm using the calculator values for now. Now, what that allows us to do is to work out the MR of the hydrated salt. That's the trick here. So it's mass over moles, which is the 1.654 of the hydrated acid. As you can see up at the top, that's what we started with. And you divided that by the moles we just worked out. So that gives you 125.96864 grams. Again, I'm sticking to calculator values for now. So keeping all the information at the side, I'm just going to sort of highlight the H2C2O4.XH2O because we're going to look at different parts of this formula first of all. So let's just focus on the H2C2O4 initially. Now we want the mass of that present in the sample. It's not going to be the 1.654 because there's obviously some water crystallization. We're separating those two parts of the hydrated salt out. So adding up H2C2O4 just on its own, it adds up to 90 grams per mole. So you multiply that by the number of moles of hydrated salt that we've just worked out. So the hydrated salt and the anhydrous salt will have the same number of moles because there's only one of these present, one H2C2O4. This is the thing we're trying to get. So now what you do is you take the original 1.654 grams and from that you subtract the amount you just calculated. So by difference you can work out how much water you've got. So you've got two masses there. Now we know what the number of moles are for this already. We worked it out over here, didn't we? So what you've got to do is take the moles of the mass of the H2O and convert that into moles. So that's mass over mR, and that gives you 0.026237628. So what you do is you line those two numbers up. That's your mole ratio. Divide by the smallest number, which is obviously going to be the one on the left, and that gives you this value. Now that can be tidied up by rounding up to 2, which means our value for x is 2. Okay, I hope that this was a useful look at this type of calculation. They do come up from time to time. They're usually meant to be quite challenging. So you wouldn't see one in a first year paper, but you would start seeing them in second year papers. Okay, thanks for listening. Until next time, see you soon.